All right, today I thought I would step you through a quality example showing you how to make a variables control chart, also calculate capability and defect rate, all for the same problem. So to do this, I wanted to give you something somewhat realistic. So I just searched online for an engineering drawing, and I thought we'd start there and explain how this process might work. So I'm going to share my screen and share a picture of this engineering drawing that I just found on the internet. You can see the URL there. Essentially, this is a drawing of a part that's round. You can see a picture of it here, and then here's a cross section. So it's like a collar of some sort. And if you've never looked at an engineering drawing before, each of these dimensions tell us something about the drawing. So for instance, this tells us how far apart these two holes should be, and presumably they're all the same. This tells us something about the different dimensions on the object. Some dimensions probably make a big difference, and some are probably smaller. You can get an idea of the tolerance limits or specification limits by looking at the two sets of numbers. So for instance here, this tolerance refers to this dimension here on the collar, but you'll notice that it has kind of a large tolerance limit, 36.0 and 35.5, so that's 0.5. Something that matters more because something's maybe nested in it or it's a contact surface will have a tighter tolerance. So for instance, this dimension in here, from here to here, probably has something sitting inside of it. So you notice its tolerance is only 0.15, is the difference between 44.60 and 44.45. So you have these different dimensions, and some matter a lot and some don't. Now, you can monitor and measure every dimension on a product like this, but that's expensive every time you measure something. So usually what companies do is they pick the things that are most critical to the function of the product, and then they'll measure those and chart those. So what maybe looks important? Well, like I said, I just found this picture online, but this dimension here looks important to me. This is a hollow hole that goes all the way through the center of the object. And this hole probably has something inside of it. So the dimension matters. And if you look here, the dimension is 20.00 to 20.13. What that means is that if it's smaller than 19, then it's too small, or sorry, smaller than 20, then it's too small. So like 19.19 or 19.99 would be too small and it wouldn't be an acceptable part. If it's bigger than 20.13, then it's not an acceptable part because it probably doesn't fit snugly enough. And dimensions you see like this where they have a round number on one side to something kind of obscure on the other, usually are parts that mate against another part. They fit together and you want them to be tight. So what you would do is you say, well, this dimension is really important, so we're going to measure this dimension and then construct a control chart from it. So that's what I'm going to show you how to do online as an example. We're going to construct a control chart for this dimension on this part. So the specification limits are it needs to be between 20.00 and 20.13. All right, so now I'm going to share an Excel spreadsheet that I've made that says, so here's what we would do. We would say, let's measure, say, 5 of these parts a couple of times a day. So you want to, if you're putting together a sampling plan to build a control chart, you want to minimize the variability within the sample and maximize it between samples. So if I want the minimum variability in a sample, I'm just going to pull 5 parts in a row as they come off the assembly line. So I pull 5 parts in a row as they come off the assembly line, I measure that particular dimension, and I have 5 measurements, right? Here's the first measurement, 20.5733, then 20.5868, 20.607, 20.06219, 20.0613. I misspoke on one of those, 20.0607. All right, and then I do that for, we've done it 25 times. So I have 25 samples, each with a sample size of 5. So the sample size is 5. And if I had more samples, if I collect data for more days, I would just append that data to the bottom here. Oh, it looks like I only have 24. I said 25, so I'll just create a 25th one. I'll show you later if maybe how I created this data. but it set up so it changes dynamically. So we're going to cut and paste it into this new spreadsheet. I'm just going to paste the values, not the formulas. All right, so we'll work with these numbers now. They changed from the previous slide because I was generating them, but now they're done. So these are fixed. 25 samples, each with a sample size of 5. Now, to make a control chart, a variables chart, we actually make two different charts. We make an Xbar chart and we make an R chart. The Xbar chart charts the mean of the process, and the R charts the range of the process. And remember, what we're mostly interested in here is whether the process is behaving in control, meaning there's not special or assignable causes affecting the process, causing it to be off. And there's two different ways the process can be off. One is the mean can be shifted, so it's not what it's supposed to be. The other is that the variance could increase or decrease in a way that we're not expecting, indicating the process is in control as well. So you make both an Xbar and an R chart. Now, the first thing you do to do that, now the first part we've already decided, right? We decided which dimension we're going to measure. I showed you that on the engineering drawing. The next step is we decide how often we're going to sample and how many measurements we're going to do, which is usually a function of time and cost. So I already decided that we're going to collect samples of size 5, and I've got my first 25 samples. I believe the process is relatively stable, so we're going to go ahead and do this. The first thing I'm going to do is find the mean of each sample, which we denote with an Xbar. So I'm just going to write Xbar here. This is the mean of each sample. So I'm just going to find the average of this row. Now, you don't have to put it in rows and columns. You could put it in columns and rows. Be sure what your samples are if you ever do this. But in this case, I have a sample size of 5. So I have 5 observations within my sample. And now I know the average of those 5 observations. The average of those 5 numbers is 20.6108. I'm just going to drag and drop that. You can see why we like to use spreadsheets. I also need a range. R stands for the range of the sample. So to find the range, I'm going to find the maximum of those 5 measurements, and I'm going to subtract the minimum of those 5 measurements, and that's going to give me the range of the 5 measurements. So in this case, it's 0.002317. And then I can find all of my sample ranges by just dragging down. All right? So those are all of my sample ranges for this part that I've measured. Now, if you recall from the book, the first thing we need to do is find the control limits now. Now to do that, I'm going to need the average mean of the samples, and I'm going to need the average range. So we call that the X double bar. I'm going to write X bar here. Equals, and then right here I'll actually calculate it. It's the average of all of these numbers. Now I need the average range as well, so I'm just going to drag that over and it will do that column for me. This one, though, is going to be equal to the R bar, or the average range. All right, so now I've got my X double bar and my R bar, and I'm going to now switch cameras. All right, so this camera is backwards. All right, so sorry about that. Now it's not mirrored. This is a table, so to construct control charts, you use these two equations. Let me zoom into these just a little bit. All right, so the center line for your X bar chart is going to be equal to your X double bar. Your upper control limit and your lower control limits are going to be equal to X double bar plus A2R bar and X double bar minus A2R bar. For the R chart, where you're tracking the variance and how it's moving, you have the center line is R bar, the upper control limit is D4 R bar, and the lower control limit is D3 R bar. Now, what are those table values? Any book that teaches how to make control charts is going to have some sort of table. In our textbook, this table is here on page 171, table 9.1, control chart constants, and it's based on the sample size. The larger the sample, the smaller the constants. So for the A2, for the X-bar chart, we have a sample of size 5, so our A2 value is going to be 0.577. Our D3 value is going to be 0, and our D4 value is going to be equal to 2.115. These numbers will be the same in any table in any textbook. They may round slightly differently, but they'll be basically the same, essentially the same numbers. What they are is there's something that converts a range estimate into a standard deviation and then moves out about 3 standard deviations from the mean. And that's where the numbers kind of come from. And then when Walter Shewhart developed control charts initially, that was something that he kind of advocated the use of. All right, so now I'm going to go back to sharing the screen, back to the Excel spreadsheet. All right, so now we know how to do this. I'm going to do some things on my spreadsheet just for convenience, because I know that I'm going to need the space for this. All right, to make these charts work, it's sometimes helpful to have the sample number right here. So I'm just going to cut and paste it here. I'm going to paste it there too, because I'm making 2 different charts, remember. All right, and then I'm going to have a center line, an upper control limit, and a lower control limit. For the R chart, I'm going to have the same thing. A center line, upper control limit, lower control limit. This will be for my X-bar chart. This will be for my R chart. All right, so the center line, as you recall from the textbook, is just X double bar, which we just calculated down here. So I'm going to just refer to that cell. I'm going to hit F4 to make that absolute. And then I'm just going to copy and paste it down. By putting those dollar signs around it, making it an absolute reference, $H, $29, means it always refers back to that one cell. I'm going to do the same thing here for the center line for the R bar chart and copy it down. All right, now the upper control limit was equal to A2, which is this value here, which I just copied, plus, it was equal to X double bar plus A2 times R bar. A2 was 5.77, and R bar is just this value here. So that's my upper control limit. To find my lower control limit, it's just X double bar minus A2, which was 0.577 times R bar. I don't have to make those references absolute because I have a whole column that matches up with this column. So that's done. For the upper control limit for the R chart, it was X double bar times D4, D sub 4, capital D sub 4. Capital D sub 4 was 2.115. And copy that down. And the lower control limit's actually easy because it was still R bar times 0. It was D3. Anything times 0, 0, but that's a bunch of zeros. All right, that's everything I need to construct the control chart. Because I arranged it such that I have the samples there, I'm going to just block that data, insert graph. Usually a line graph works. Let's see. Sometimes my Excel asks. That's funny for me. All right. So that is my X bar chart for this data. I think I made a mistake because let me delete, well, I can leave that, I don't need to delete it. I can tell I made a mistake because the distance between the lower control limit and the upper control limit should be exactly the same, and they're not. So here's my center line, or between the center line and the upper limit. Oh, there we go. My decimal's in the wrong place. Nice. I need to copy that all the way down. Much better. All right. Now, first off, this is really, really out of control. You can see it's really out of control because it's initially below the lower control limit, and then it jumps up above the upper control limit. Let's go and do the R chart too. Same thing, I'm just going to insert the chart type. All right. Now, if I want to put in the titles, this is the X bar chart. This is the R chart. All right. Now, when you interpret X bar charts and R charts, you interpret them together because they're two different views of the same process. In this particular case, if you look at this, the R chart kind of looks okay for a bit. Looks a little funky here, but there's probably not a specific, you're not certain it's out of control. But then this gives me some cause for concern because these spikes are so high, almost above the line. But there's nothing for sure that says this process is out of control on this R chart yet. On the X bar chart, on the other hand, it's a complete mess. So we can kind of see it's out of control. Let me show you how I actually generated the data. If I look up here, the data was generated from a normal distribution with a mean of 2.06 or 20.06 and a standard deviation of 0.0017. If you don't know how this works, it's not that big a deal. What I did down here, though, at 0.9 is I artificially increased the standard deviation a very small amount. All right. And then at time 18, time 19, I also increased the mean by a small amount, and I increased the standard deviation a little again. But the interesting thing is it took it a long time to figure that out. And I apparently made the jump maybe too big. Let's do something just for fun, because you've seen how to do it now. I'm actually going to drag that down. So I just removed that shift in the mean. Let's see what happens when we change this in our other spreadsheet, what happens to the charts. So this is a completely different set of data, but for the same feature on the same engineering part, I'm going to paste it doesn't like me to do it. Not sure why that happened. And here again, Control C, paste special values. All right, so they're the values. So the whole thing changed. Now, before, the process was really out of control, and it found it very, very easily because that shift in the mean was too big. Now we have no shift in the mean, but we do have a shift in the variance. Now, if you look at the charts, it's a small shift in the variance. What you see is that the X-bar chart really looks okay till right here, and then we have a point that's clearly too low, followed by a couple of points that were probably too low and probably too high here. Now remember, the variance shifted at 0.9. It increased a little bit. Here in this chart, we go to 0.9, and then you see an increase in the variance. You still don't see it, but the Xbar chart showed me that it's out of control. So I would classify the process as being out of control. And it is in fact out of control because that's how I designed the data. That's how you would construct a control chart. All right. Hopefully that was easy enough to follow. I wanted to take the next step though, and now also calculate the capability of this process. So for instance, if this was a vendor and I was trying to evaluate whether they were capable of making this product or not, they would send me maybe a bunch of sample parts. So this is 100 measurements, 5 times 20. So they sent me 100 parts, and they said that the parts came off sequentially off their line in groups of 5, and then they took them a little apart. So they could do the sampling for me, send me the parts. To do Cp Cpk, the capability ratios, there's 2 different ways. I need the standard deviation. There's 2 different ways to find the standard deviation. We're just going to actually calculate the standard deviation for all these parts. There's another way, but it's not in our textbook, so I'm just going to show you this way. STD, DEV, forget the formula. There we go. And I'm just going to block the whole data set. All right. So this estimates the standard deviation. Now, you recall the actual standard deviation, because I just showed you that data, is 0.0017 for the first 8 sets of points. I guess it's 25 times 5, so it's 125 points. And then for the last 16 data points, it's 0.0024. So you'd expect it to be between there. The CP ratio is given as the upper specification limit, which was 20. I guess I'll just type these in actually, make it simpler. So the upper spec limit was 20.13. The lower specification limit was 20.00. All right. The CP ratio is equal to the upper specification limit minus the lower specification limit divided by 6 times the standard deviation of the process. We just calculated there. All right. I'm looking to make sure I didn't make a mistake because that number seems too high. I guess it's not. Okay. So this is a very capable process. You want the CP to be, the CP and CPK to be greater than 1. Now, the CP makes the assumption that the process is perfectly centered. It's the upper bound on your CPK. The CPK can never be larger. The formula for the CPK is given as the minimum of the upper specification limit minus the mean of the process, which would be the X double bar in this case, divided by 3 times the standard deviation of the process. I should put another set of parentheses. And the X double bar, the mean of the process, minus the lower specification limit, divided by 3 times the standard deviation of the process. And it gives me 9.03. So this process is highly capable. Now, just for fun, instead of calculating the standard deviation directly, I'm just going to put in a number so you can see how this behaves. If I put in 0.2, well, if I put in 0.2, it's going to be horrible because the variability is way too high to hold those tolerance limits. If I put in 0.02, now it gets down to where this would be an interesting situation. So the Cp is 1.08 and the Cpk is 0.999 essentially. What that means is if the process were perfectly centered between the specification limits, it would be capable. But because it's not quite capable, but it's close. That would be how you interpret this. Change this back. But that's how you calculate the Cp and the Cpk and interpret them. This is also how you would construct an Xbar chart and an R chart, and you might interpret them. And I hope this example proves useful to you as you try to solve a few of these problems yourself. All right. Thank you for watching, and I hope it proves helpful.